Hello, so now we are testing A star. So let's input graph D into the system. So let's return to the main menu, let's go on A star, and so we have 4 nodes. Edge AB has a weight of 2, edge AC has a weight of 3, edge AD has a weight of 3, edge BC has a weight of 0, BD has a weight of 1, CD has a weight of 5. Please enter your start node, so we'll say that's A and our end node is D. Now the x coordinate of our end node, well, our end node is D, so its x coordinate is 1. The y coordinate of our end node, well, that's a 0. The x coordinate of node A, so that's a 0, and the y coordinate of node A is a 1. The x coordinate of node B, well, our coordinates of node B are 1, 1, so there we go. And the x and y coordinates of node C are 0 and 0 respectively. So, and node D was our end node, so we already entered that information. So this is what they found. Let's have a look to see if it's what we expect. So the shortest distance should be 3, which it is. The path should be AD, which it is. And there are no alternative shortest paths, so that's good. And I accidentally closed the window, sorry. But yeah, so that works. And you can see that we could have gone from A to B to B to D if this was just Dijkstra's, if there weren't any nodes. But with the nodes, there's definitely a change in how things work. So we can pass this, and I'm going to have to rerun the optimization. Sorry. Here we go. So now task number 22 is checking graphs with no direct connections, and we're going to use graph B, which I remember, so I'm not going to go back to it. Regarding the coordinates, we're just going to give random coordinates. So A is 0, 1, B is 1, 1, and C is 0, 0. I don't know where this 1, 0 comes from. I'm really sorry about that. So 0, 1, 1, 1, 0, 0. Okay, so if I A star, 3 nodes, 5, 0, 0. So our start node is A and our goal node is C, and our end node has x coordinates, so 0, 0. So let's put that in. Node A has x and y coordinates 0, 1. So let's put that in. And node B, 1, 1. So let's put that in. And we get that the path isn't reachable, which is exactly what we want. And as with the other ones, I also want to see what happens if I do A to B. So 3 nodes, again 5, 0, 0, A to B this time, x coordinate of my end node, so the x and y coordinates are 0, 0, the x and y coordinates of node A are 0, 1, for node C are 1, 1. Yeah, no, sorry. Oh, I've done this wrong, haven't I? Yeah, I've done this wrong. Let's try that again. That's my bad. I got a bit confused. Sorry about that. Let's try again. So 5. I don't think it will have made an entire difference. We still should have gotten a path from E to B. But just for consistency's sake, let's make sure it's the right thing we've entered. So end node this time is node B, so that's 1, 1. Node A is 0, 1, and node C was 0, 0. Good, that's good. Okay, wonderful. So we can see that A star also responds exactly the same way as how our first 2 optimizations responded to an awkward graph. Now, we can move on to Bellman-Ford. let's have a look. Yep, we've got 5 more minutes. So, Bellman-Ford. Now this time we want to redo an edge check, because as we discussed previously, we excluded Bellman-Ford from checking the weight of each edge because negative values were acceptable. So I'm just going to check -9.7 and -5.75, and they should all be accepted because they are all valid entries. So if we return to the main menu, and if we decide to do Bellman-Ford, and let's just say, well, we asked for the weight of each edge first. Let's just go with 4. So 1, 2, 3, 4, 5, 6. So doesn't matter. So is there a path? Oh, all of this as well. Oh, I'm so sorry. I am so sorry. We're checking for the edges, aren't we? Sorry. Let's try again. I don't know what came over me. Let's do 7 then, because it makes it easier. So edge AB, so let's put -9. That works, that's wonderful. Edge AC, 7, that also works. And -5.75 also works, so that's good. Now let's check some invalid entries. So let's try D and negative inputted. So please enter a valid edge weight, negative inputted. Please enter a valid edge weight. So we can confirm, we can pass these tests. Now we want to test the optimization itself. How long do we have? 4 minutes. So testing Bellman-Ford, we're going to be using graph E, which looks like this, and our start and end nodes are A and D, and this is our expected result. So let's try this. Let's come here, let's return to the main menu, let's go on Bellman-Ford, and we have 4 nodes. Let's open up the graph as well, that would help. Edge AB is 5, edge AC is 1, edge AD is 7, edge BC is -2, edge BD, I've done that wrong, haven't I? I'm very sorry. Let's try again. 4 nodes, my apologies for that. Edge AB is 5, edge AC is 1, edge AD is 7. Now BC is 0, yep. BD is -2, CD is 2. Okay, our start and end nodes are A and D. So is there a path from A to B? Let me just check the time. We've got 2 minutes left. A to B, yes there is. A to C, yes there is. A to D, yes there is. B to A, no there isn't, because the arrow only goes from A to B. B to D, yes there is. C to A, no there isn't. C to D, yes there is, sorry. D to A, no there isn't. D to B, no there isn't. Alright, so D to C, one last one, no there isn't. So we get this results tab, so let's compare it. So we should have had a shortest distance of 3, which we do. We have a path of ABD, so the path being ABD, or ACD. So ABD and ACD. So that has passed, and it's almost 10 minutes. So I'm going to end this video now, and we will do test number 26 in the next video. So this test has passed. The optimization works for, well, Bellman-Ford works in the system for these sorts of graphs. So I will see you in the next video.